Hi everyone, my name is Zachary, and today I'm going to present what I plan to bring to the EPSCoR 2022 conference, that being polysolid ether-based nanoparticles for use as potential nanocarriers. Quick outline before we get started. We'll talk about the synthesis of the polysolid ether-based polymers, then into the synthesis of the nanoparticles, the size comparison of said nanoparticles, and then a little bit into the drug loading that we are currently working on. Pictured here is the synthesis for the four polymers that we're using, the PG200, PG400, and PG1000 PSCs, as well as the 1,6-hexanediol PSE. And of course, this PSE comes from the solid ether bond present here in all of the polymers. A picture here are the catalysts that we are using for more efficient synthesis. Here we have the schematic for the nanoparticle formation, and this is done through a process known as nanoprecipitation, where the polymer pictured here will be dissolved in a solvent. We're using acetone and diluted with water and heated to 50 degrees Celsius for about 48 hours long for the acetone to evaporate off and for the polymer to reform into the nanoparticle. And we get a few different sizes based on the polymer that we've used for that. So the 1,6-hexanediol is about 130, the 200 at about 140 nanometers, the 400 at about 120, and the 1,000 much smaller at the 40 nanometer range. And here is the PDI, polydispersity index of those, just indicating through the smaller width of these peaks that these are more concise data, and there's no discrepancies in the size of these nanoparticles. Pictured here is a schematic of the drug loading that we're currently working on, in which we're adding the drug at the same time as the synthesis of the nanoparticle during the nanoprecipitation, allowing for the formed nanoparticle to have these drugs loaded onto the surface. And this is important because of the solid ether bond's ability to degrade in more acidic conditions that we see in cancerous cells compared to regular cells. So theoretically, this would enter the cancer cell, degrade, allowing for the drug to disperse off for drug treatment of the cancer cell. And this would theoretically not be seen in a healthy cell, as the conditions wouldn't be acidic enough for this induced degradation. So conclusions, well, we were able to successfully synthesize the PSE polymers and nanoparticles, and we got a few different sizes based on that. So if we need a specific size of nanoparticles, that would essentially dictate the polymer that we would choose for the synthesis. And into the future work, we're going to work on the degradation studies of these nanoparticles, as well as looking at that pH-induced drug release. As well, we're going to further functionalize the PSEs with the possible addition of photosynthesizers. Of course, my acknowledgments, UND, of course, for giving me a spot to work, and EPSCoR and NSF for funding my research. Here are my references. Thank you for watching.